Good morning, everyone. I am Vinita, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College.
Yeah, today in this lecture, I am going to explain a topic in power system transients that is from Unit 5, short line or kilometric fault. First, let us see the definition for short line or kilometric fault. And a short circuit that occurs on an overhead line at a relatively short distance of 0.5 to 5 kilometer from the load side of the circuit breaker is called short line or kilometric fault. When this type of fault occurs, which imposes heavy duty cycle on the circuit breaker, thereby affecting its interrupting capacity. That is, it will take more time to interrupt the circuit breaker operation. And here we will consider an example for the analysis of this kilometric fault. Here, this is the transmission line which consists of a transformer, a circuit breaker, and a transmission line. At the end of the transmission line, just let us assume the fault has been occurred. And if the fault occurs, what will happen? Normally, in all the power system, we will be providing the impedance to control the fault current. Here also, the impedance that will be added in the circuit to limit the fault current. See, when a short circuit fault occurs at some distance along the transmission line from the circuit breaker, the line impedance which limits the fault current, thereby generating the circuit voltage. So all of you know the procedure. Whenever the circuit breaker contacts get open, what will happen? There is a development of voltage across the circuit breaker. Here also, by providing the impedance, we will be limiting the fault current so that obviously the voltage across the circuit breaker contacts get developed. This generated voltage, which is divided on either side of the circuit breaker in proportion to the impedance of the source and the load side. That is, with respect to the impedance, the voltage that is the generated voltage that will be divided in the source side as well as the line side. That will be shown in this diagram. Here, this is nothing but the line side and this is nothing but the load side. So if the fault has been occurred, the circuit breaker contacts get closed, and so that what will happen? Here the fault is occurred, and here this is the position of the circuit breaker. When the circuit breaker contact gets fully opened, here the generated voltage will be maximum. At the same time, here the reactance value as well as the current value, that is equal to 0. And this is the breaker position at which this is the corresponding voltage at the circuit breaker. So depends upon the impedance value. Here we will be getting the voltage at the source side as well as the line side. Let L be the source inductance and L1 be the line inductance to the fault and C1 be the line capacitance to the fault, where and E is the peak value of the EMF driving the fault. Peak voltage at the breaking point is given by V is equal to L1 divided by L plus L1 into E. How to calculate the value of the voltage at the circuit breaker point? So V is equal to its opposite inductance divided by the total inductance into E. So just like current division technique, here we'll be using the same relationship to calculate the value of the voltage. So V is equal to opposite inductance divided by the total inductance into this total voltage E. Now, during faulty condition, we know that the total voltage, that total current, that is equal to 0. So how we are getting the total current that is equal to 0? Opening of the circuit breaker is simulated by injecting a cancellation of current. So here the magnitude of current which is given by E by omega into L1 plus L plus L1 into omega t, that is equal to, this is the magnitude of injecting current. So here this will get this omega and omega get cancelled, so that we can write the expression as E divided by L plus L1 into T. And here this is nothing but the magnitude of the cancellation current. Here this is the magnitude of the input current. So the total magnitude is nothing but after cancelling this omega, we will be getting E divided by L plus L1 into T. So the same magnitude, same amount of current we have to inject it in the opposite direction. So the magnitude is nothing but that is the magnitude of the injecting current is minus E divided by L plus L1 into T. And this current wave traveling on the line produces a voltage wave. So what is the formula for voltage? V into V is equal to I into Z. So here we have seen the magnitude of V is equal to magnitude of I is equal to E divided by L plus L1 into Z. For a particular time period, we have to multiply the expression with T so that we can calculate the voltage, that is voltage magnitude of the voltage wave, and where Z is the surge impedance of the line. And we know velocity of the light, that is equal to 1 divided by square root of L1 into C1. So the traveling wave that will be travel in the same speed of light. So that's why we are using the same formula here. V is equal to 1 by square root of L1 C1. And we know surge impedance Z is equal to square root of L1 divided by C1. Now we have to write the formula for T. The time taken by the wave to reach the faulted end, which is represented by T, is given by square root of L1 into C1. Now we have to substitute all the values in your previous expression. That is, in the voltage equation, we have to express all the. So this is the voltage equation. In this voltage equation, we have to substitute the value for T as well as Z. So that what will happen? So the magnitude of current is minus E divided by L plus L1 into T into Z. So what is T? T is equal to square root of L1 into C1. What is Z? Square root of L1 divided by C1. Just we can simplify this expression. So what will you get? If you simplify this one, L1 and this, so here, sorry, the C1 and C1 get cancelled. And here you will be getting square root of L1 square. So if you take it outside, you will be getting L1. Therefore, the magnitude is given by minus E divided by L plus L1 into L1. That is equal to, this is nothing but magnitude of minus V1. Already here we have seen the magnitude of V. It is L1 divided by L plus L1 into E. Now we have calculated another value of V, that is equal to minus E divided by L plus L1 into L1. So what is this one? It is nothing but minus V. Now during this faulty condition, that is before the opening of the circuit breaker, when the short circuit occurs, the total voltage that is equal to 0. Therefore, V plus V that is equal to 0. Now, the voltage wave which is reflected with opposite sign at the short circuit point and with the same sign at the breaker terminal. Now, this is the waveform that is drawn between voltage as well as current. So, the magnitude of voltage is nothing but E into L1 divided by L plus L1. And the value of voltage which will vary from plus V to minus V within a short period of time. So, this is plus V, this is minus V. So, it will travel from plus V to minus V within a short period of 2t. So in this time, the order of other terminal of the circuit breaker would be still having a potential which is approximately equal to V. Now, if the source can be represented by a parallel L and C circuit, the source side response will be 1 minus cosine times the recovery wave with a period of 2 divided by 2 into square root of LC, and amplitude which is given by E minus E divided by L1 plus L plus L1 into L1. So this is, that is, after taking LCM and all, we will be getting the final expression as E divided by L plus L1 into L. Therefore, the potential, if the circuit breaker terminal on the source side is given by E divided by L plus L1 into L into 1 minus cos of T divided by square root of LC. Now, Here, after opening the circuit breaker, that is once the fault is clear, the circuit breaker contacts has to open. So during opening, the recovery voltage that will be developed across the circuit breaker. So how to calculate the recovery voltage? So recovery voltage is nothing but the difference between the input side as well as the output side. So if you take the difference between these two voltages and if you draw the characteristics between the two voltages, we will be getting the characteristics like this. So this is the recovery voltage characteristics when the circuit breaker contacts gets open after clearing the fault. This is about short line or kilometric fault. Thank you.